Hello, everyone. Welcome to Chapter 2. This should be a fun chapter. Let's see. We're going to start with systems, feedback loops, elements of life, definition of acids and bases, and the four categories of organic molecules. Okay. So essentially, a little bit of environmental science and a little bit of chemistry. Let's see. All right. So, what's a system? A system is a network of interdependent components and processes with materials and energy flowing from one component of the system to another. So, this is vague because a system does not have to necessarily be a biological system. It could be a computer system, it could be an administrative system, it could be um, a, a, uh, a population, anything that has a process and energy flowing through it is considered a system. Okay. So now we have to be a little bit more specific. An ecosystem is a complex assemblage of animals, plants, and their environment through which materials and energy move. A biologic, in another words, a biological community and its physical environment. Okay. So if we're in a classroom right now, the population of students and the room that encompassed it could be considered an ecosystem. Or faculty, staff, and students, and the campus would be considered an ecosystem. Or the population of Common Falls and the city is buildings can be considered an ecosystem. Or the local river, the population of fish and insects and diatoms and the surrounding trees can be considered an ecosystem. So I'm listing all this in order to get you to understand that um, an ecosystem, even though it's a biological community and has physical surroundings, has to be defined. And the reason it has to be defined is because usually when you're studying an ecosystem, uh, you're going to be um, you're going to be recording information about that ecosystem. And so you have to define to your audience what it is that you're looking at, what it is that you're studying. Okay. So here's a cycle in an ecosystem. Okay. You have primary producers, a plant. You have secondary producers. This is called a trophic level. Okay. Troph means to eat. So we're going from plants to herbivores. And then that herbivore goes into a omnivore, okay, a fox, and then finally that fox will eventually die, and decomposers will recapture that protein and that energy back into the system in order to provide nutrients for future plants. So here's a complete cycle in an ecosystem. I think I said omnivore. Probably carnivore is a better adjective. Okay. Now we have different types of systems. We have open systems, okay, and we have closed systems. So open systems are systems that allow the exchange of matter and energy with the surroundings. And as it implies, a closed system is exactly the opposite. It's any system that does not allow the exchange of matter or energy with the surroundings. Um, a long time ago, you could order an ecosystem from Edmund Scientific, okay? And what you would get is you would get this glass globe. You'd get a little, what is it that I'm looking for? You'd have a little twig in there, and it would have a shrimp, and it would have a two or three animals that lived in a community. And effectively, if you can believe this, they were supposed to function just like this. One would perish, and it would become the food of the next one, and it would become the food of the next one, and then decomposition would take place. And effectively, if you took care of this ecosystem, it was literally covered, completely covered. No, no oxygen or anything came in or out of it. And by taking care of it, it meant that you exposed it to sunlight a certain amount of time, and you kept it at a constant room temperature. That ecosystem would continue to thrive for a long, long time, for years, which is mind blowing because, again, you're talking about a little glass globe that's about a foot in diameter. Um, Kids are no longer interested with ecosystems, so I'm sure it's not for sale anymore. But the reason I'm bringing that up is because that's a perfect example of what we picture when we talk about a closed system. Okay, a space station, for example, would be a great example of a closed system. Why? Because no energy or matter is exchanged with the surroundings. Now, hopefully, somebody out there is jumping up and down and going, "You're lying! You're lying!" There is exchange of matter and energy with the surroundings. You just finished saying that you put the closed system next to sunlight. Then it's harvesting energy from the sun, and therefore there is actually energy going into that closed system. Absolutely correct. Absolutely correct. As a matter of fact, it's almost impossible to form a true closed system. It really is. It's more of a philosophical construct more than anything else. But again, what we're trying to define is something that comes as close as possible to not exchanging energy or matter with the surroundings. Okay. Throughput. This tells us how much energy and matter is going into, through, and out of the system. Okay. Um, Really, the birth of this comes back to limnology, the study of lakes. Okay. Not too long ago, a few decades ago, there was a young man that was disabled, and he could not do field work. So instead of going out there and doing the usual collections involved with natural resources, what he decided to do is make a study of a lake based on the materials that went into it and the energy that went into it and the materials that were produced by that lake. And that discipline uh, was the discipline of limnology, the study of uh, freshwater lakes, was born. And now, now you can't look at an ecosystem without doing that kind of a study anymore. But the reason I'm telling you this is because it's through limnology that we first came out with the concept of throughput, a measuring of the amount of biomass and energy into and through a system. Okay. Okay. So as we addressed at the beginning, systems function in cycles, and you can have what's called a positive feedback or a negative feedback loop. Okay. Um, the one that we encounter most commonly in nature is what's called a negative feedback loop. Positive feedback loops are not good. Okay. So let's imagine that you're in your little house and it's winter and you have your little, oh, let's make a different color here. Let's make it red. There we go. And you have your low thermostat, and you set it to what? If you're an energy saver, you save it to 65 degrees. But most of you probably set it to room temperature. So let's say you set it to 72 degrees. Okay. What you may or may not have realized is that you have just started a negative feedback loop. Okay. Once you have set this, what's going to happen is that the temperature in your house is going to decrease. And it's going to decrease a little bit below 72 degrees, just a little bit below. But as soon as that happens, your thermostat is going to become aware that it's too cold, and it's going to turn your furnace on. So now the temperature in your home is going to start going up, nice and slow. And as before, we're going to overshoot that 72 degrees. So we're probably going to reach 75, something like that. And then the thermostat is going to go, okay, it is too hot. Time to turn the furnace off. So your house is going to be here, and then after a while, the temperature is going to start falling down again, and it's going to fall below 72 degrees. Your furnace is going to turn on. Your temperature is going to go back up. And so this is what the temperature in your house is going to look like. In math, we call this a sinusoidal curve. Just goes back up and down, up and down. And what your thermostat is trying to do is trying to maintain an average of 72 degrees. That's what it's trying to do. Sometimes it goes a little bit above, sometimes it goes a little bit below, okay? Why am I discussing this? Because this is the very definition of a negative feedback, okay? You go in a certain direction and then something happens so that we go in the opposite direction, negative the direction that we're going before. And then we're heading in one direction and something happens to change your direction again. So it's a negative of the direction that we're going with in the first place. And then we're in a new direction, and then something happens to change that direction in a negative direction. That's negative feedback. And what that allows us to do is maintain, for lack of a better word, homeostasis in your home where the temperature is pretty close to 72 degrees. So in nature, negative feedback is more common than positive feedback because nature, not unlike ourselves, likes to work within narrow parameters, right? So we're going to be talking about water in a little bit probably. And let's say that the sun comes in the morning and the temperature on the earth increases. Now, instead of doing this, going straight up, it's going nice and slow. Why is it going nice and slow? Because we have oceans that are functioning as heat sinks and taking all that energy from the sun, okay? And then as the earth rotates, okay, the temperature is going to stay, is going to remain the same. Then it's going to become night, and then the ocean is going to release all that energy into the atmosphere. And it's going to, so the atmosphere is going to cool, but not very quickly because the ocean is keeping it warm. And then the next day comes in and the ocean gets hot again. And then during the night, the ocean releases the heat to the atmosphere, and the atmosphere becomes cold because it's night, but not as cold as it could be if the ocean was not releasing its temperature. You see that? Is that beautiful? So we end up again with this beautiful sinusoid that keeps the average temperature of our world within living conditions. Okay. Now, positive feedback, that's not so good. Positive feedback implies that something goes in one direction, and then there's drive to make it go in that direction more and more and more and more. That is not good. It doesn't matter whether you're describing population, it doesn't matter whether you're describing a pandemic, it doesn't matter whether you're describing anything. There's very few instances in the world where a positive feedback loop is a good thing. Okay, in biology, we only know of two examples. We only have two examples, and one of them has to do with childbirth. Okay, when a woman is experiencing childbirth, uh, uh, her brain releases oxytocin, and that oxytocin, what it does is it increases the contractions, and as the contractions increase, more oxytocin is released, which increases contractions, which increases the oxytocin, which increases the contractions, and you might think something terrible is going to happen, something's going to blow, and effectively it is, and what it is going to be childbirth. And then once the child is born, then all of a sudden this comes back down over a period to normalcy. Okay. But typically we do not have positive feedback loops taking place in the world. Okay. So positive and negative feedbacks. We typically see negative feedback loops more frequently. Okay. This is something interesting. Your author calls it emerging properties. Okay. It's very strange. Um, so it says when the characteristics of a whole system are greater than the sum of its parts, that's called an emergent property. And here's a picture of mangroves. So mangroves are incredible trees for many reasons. Number one, it provides a place for nascent species to grow. So crawdads and fish and frogs and I mean a diverse system of organisms use mangroves as a place to grow and then end up going into their adult species out into the open water. But if it wasn't for this mangrove tree is effectively the is a cradle of all these different species. So not one, many, and consequently, it is very important. Another thing that mangroves do, which is very interesting, is I don't know if you can tell what's going on here, but they put a little mangrove tree out here, and then soil, sand, sediment attaches to that little seedling, and over time, this becomes land. So mangroves are literally the only plants in the world that carry out land reclamation. In other words, they actually produce their own soil. No other plant does that. So mangroves are from an environmental standpoint are incredible. But if you're going to develop the next strip mall, mangroves are an eyesore. So whenever there's a development, the first things that take it are these poor mangroves. And I got to tell you, it's a terrible thing. Um, let's see. I'm trying to see if I forgot anything else to tell you. Provides countless indirect economic values, propagation routes, trap sediment and stabilize mud flats. Um, It improves water clarity. It protects offshore coral reefs from silt. It also protects small fish and other marine species. Many commercial ocean fish and shrimp species spend juvenile stages hiding among the mangrove trees. So we depend on these, okay? Um, and the forest protects the shoreline from damaging storms and tsunamis. Collectively, these services can be worth hundreds of times the value of shrimp farm, but they exist only when the many parts of the system function together. Okay, so a very good example of an emergent property. Okay, but I will tell you, everybody else in the free world calls this synergy. So synergy means that the sum of its parts is worth more, is greater than the whole. Okay, um, this definition right here. The characteristics of a whole system are greater than the sum of its parts. So you can call it emergent properties or you can call it synergy. But the point is that these are very important properties to pay attention to. Okay, we're switching to chemistry. So let me move this out of the way here. We're going to start with the principle of conservation of matter. This tells us that under ordinary circumstances, matter is neither created nor destroyed, but rather is recycled over and over again. Okay, this has a couple important points attached to it. Number one, in chemistry, the conservation of matter tells us that what you produce in a chemical reaction should be equal to what you started with in that chemical reaction. And as a matter of fact, we use this thing called a, uh, um, a balanced chemical equation in order to analyze chemical events. Okay. And again, what we end up with has to be the same number and type of atoms as what we started with. So, in other words, matter is neither created nor destroyed. Okay. The other point that the author wants to make at an environmental level is that there's no way. In other words, when we decide to uh, uh, throw away more items than anybody else in the world, there is no way. Our garbage has to go somewhere. It doesn't magically disappear. So, where's it going to go? Is it going to go to a landfill? Is it going to be exported somewhere else? Where is it going? Okay. And I got to tell you, we actually have solutions to these problems right now. They're elegant and beautiful, but for whatever reason, we're not using them yet. But this is something that is important right now, and does the fact that when you choose to be a throwaway society, up until now at least, there was no going away. Okay, let's see. Okay, so what do we have? We have elements. Okay, atoms are the smallest. Is the smallest level of matter. A means without, and Tom means cut. So an atom means that thing that we can no longer cut because we've gone as small as we possibly can. Atoms are made out of a nucleus, which contains a proton and a neutron, and negatively charged electrons going around it. Okay, so this is here's carbon. Okay, and you know what? It just occurred to me I need to put a periodic table up for you guys, but we can do this. We have the technology, or you can go to P table yourself. Go to P table, and then you can go image, and you end up with this. Okay. This is a beautiful periodic table. So let's have a quick review. Okay? Let's have a quick review. Here's our periodic table. Okay, here's hydrogen here. Let me make it bigger so you can see it. There's hydrogen. There's the atomic number 1. That means that it has 1 proton. And if it's a neutral element, it also has 1 electron. Here's the atomic weight at the bottom, 1.00794. This tells us that there's isotopes of hydrogen. In other words, there's hydrogen that has a proton in the nucleus, there's hydrogen that has a proton and a neutron, and there's hydrogen that has a proton and 2 neutrons. They are all hydrogen, but they have different weights. Those 3 variations are called isotopes. And when you average the normal availability of them, the natural occurrence it's called, you end up with an average weight of 1.00794, okay? But this hydrogen has 1 proton and 1 electron, okay? That's the part that we care about. When we go all the way to the right, the next element is helium. See the atomic number is 2. So the atomic number for helium is 2, and therefore it has 2 protons and it has 2 electrons. And helium is special. It belongs to this last period of the periodic table. See the purple guys? The purple guys are very special, very special. These are the noble gases, okay? They're called noble because they just do not play with anybody else. They are noble, okay? They're the Kardashians of the periodic table. Everybody else wants to be like the Kardashians. Okay, maybe you and I don't want to be like the Kardashians, but you get what I'm saying. So anyways, these are the Kardashians, right? And so hydrogen wants to be like helium. It has 1 electron, but it really wants to have 2. Why? Because when they fill these shells, these atoms have electrons at the lowest energy level. And that's where everything in the universe wants to be. It wants to be at the lowest energy level. You and I don't want to stand up if we can sit down, and we don't want to sit down if we can lie down. A car doesn't want to be at the top of a hill. It will gladly roll to the bottom of a hill. Everything in nature wants to be at the lowest energy level. And to get electrons at the lowest energy level, you have to have these shells full. Okay? So, hydrogen has 1 electron. It also has 1 valence electron. Helium has 2 electrons. Why? Because it has an atomic number of 2. Therefore, it has 2 protons. If it's neutral, it has 2 electrons. And those electrons are valence electrons. Now we go to lithium. Lithium has an atomic number of 3, if you can see that. Okay? That means that it has 3 protons. If it's neutral, it has 3 electrons. So how many valence electrons does it have? This is a trick question. The answer is 1. And the reason for that is because 2 of his electrons are happy. They're in a helium configuration. Those 2 electrons are at a low energy level. So if you have 3 electrons and 2 of them are happy, 3 minus 2 is 1. There's only one little guy on the outside that's going, hey, what about me? Okay. We go to beryllium. How many valence electrons? The atomic number is 4. That means it has 4 protons. That means that it has 4 electrons. But the number of valence electrons are 2. Because it has 4 electrons, but 2 of them are happy. Okay? Then we go to boron. Same concept. 5 minus 2 is 3. Are you with me? So let's recap. 1, 2 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. And then the second shell is closed with neon. Are you with me? Okay, now we're going to go to the next one. Are you ready? Sodium. How many valence electrons? If you guessed 1, you are correct. Why? Well, the atomic number is 11. That means that it has 11 protons and 11 electrons. However, of those 11 electrons, 10 of them are happy. So 11 minus 10 is 1. So this guy has 1 valence electron. Can you guess what the next one is? That should be 2. 3, 4, 5, 6, 7, 8. And then we go to potassium. Can you guess? It should be 1. So this is 1, 2, 3, 4, 5, 6, 7, 8. And then we go to rubidium. Can you guess? Still 1. 1, 2, 3, 4, 5, 6, 7, 8. Okay? And we're not going to go much more than that. And the reason for that is because we don't deal with a lot of these guys in the middle. Okay? These are transitional metals, except for iron and iodine. We usually don't deal with these. So you should keep in mind now that everything in period 1 has 1 extra electron, 2, 3, 4, 5, 6, 7, 8. We doing okay? Okay, let's go back to our table here. So here's carbon. Okay. Now, according to this, where's carbon? Here's carbon. There's an atomic number of 6. How many valence electrons do you remember? You start at 1, 2, 3, 4. So you have 4 valence electrons. Let's take a look. 1, 2, 3, 4 valence electrons. I'll be darned, look at that. Does it have more electrons? Yes, but those electrons are happy. And what's the atomic number? Oops. What's the atomic number? 6. So how many protons is it going to have? 6 protons. If it has 6 protons, it's going to have 6 electrons. How many neutrons is it going to have? We're just going to guess. It could be 6, but it could be 7 or 8. It doesn't matter. The part that makes it carbon is the number of protons. That's what makes it carbon, the number of protons. The number of neutrons doesn't matter. It makes it a different isotope, but it's still carbon. Are you with me? So what makes an element a certain element is the atomic number or the number of protons. Okay? Atomic number. Atomic mass is the sum of protons and neutrons. Again, isotopes are formed from a single element that differ in their atomic mass. Another way of saying that is they differ in the number of neutrons that they have. Okay. If an atom gains or loses an electron, they end up with a charge and is therefore called an ion. Okay. Negatively charged ions with 1 extra electron are called anions. Positively charged ions are called cations. So sodium, before we go into it, let's take a look at the periodic table. Here's sodium. Do you remember how many valence electrons? First period is 1, right? 1, 1, 1, 1, 1. So sodium, who does it want to be like? Well, sodium can lose 1 electron and be like neon, or it can gain 1 2, 3, 4, 5, 6, 7, and be like argon. I ask you, what do you think is easier, to lose 1 electron or gain 7? If you can't decide, I'll let you know it's easier to lose 1 electron. So sodium typically loses 1 electron, so it can be like neon, and when it loses 1 electron, it ends up with a +1 charge because it has 1 proton more than it has an electron. Okay? Look at that. Sodium, this thing is in the way no matter where I put it. Sodium has a plus charge. Now let's look at chlorine. Let's see where chlorine is at. Here's chlorine. So 1, 2, 3, 4, 5, 6, 7, 8. So chlorine just needs to gain 1 electron to be like argon, and it's happy. So think about it. Sodium needs to give off 1 electron. Chlorine needs to gain 1 electron. So what do? Sodium gives his electron to chlorine. Now they're both happy. But something funny happens. Sodium now has a +1 charge because it's missing an electron, and chlorine has a -1 charge because it has 1 electron too many. They have opposite charges. Do you know what happens to things with opposite charges? Click. They come together like little magnets. And that's exactly what happens here. So the positive sodium and the negative chlorine become an ionic bond, and it's called sodium chloride. Okay? So your author is going a little bit fast, but if there's a sharing of electrons, the bond is covalent. If there's a transfer of the electron, then the bond is ionic. Okay? Okay. Let's do some chemistry, okay? So here's hydrogen. Was a good, we'll write in red. Okay. So we have a hydrogen here. We have a hydrogen here. We have a hydrogen here. Right? Okay. How many valence electrons does hydrogen have? Strange. Let's take a look. We'll go back to our periodic table. Oh, sorry. I found my periodic table was in my PowerPoint. Here we go. How many valence electrons? 1, right? 1. So we're going to draw one little dot. One little dot here, and one little dot here, like so. Now, how many valence electrons does hydrogen want? Well, it wants 2, so it can be like helium. Okay? Well, can we do that? Sure. Let's have them share these 2 electrons. Sorry about that. Let's have them share these 2 electrons, like so. And now this hydrogen thinks it has 2 electrons, and this hydrogen thinks that it has 2 electrons. Congratulations. You now have what you want. So consequently, we end up with a hydrogen molecule. So now when you see a little bar between 2 elements like this, you know that it's a covalent bond, and that it consists of 2 electrons. And that's what we have here. Okay, that's what we have there. Okay, let's do hydrogen and chlorine. All right. So we're gonna do hydrogen in blue. How many valence electrons? That's right, 1. And then we're gonna do chlorine. I'm gonna do chlorine in red. Why? Because chlorine is very electronegative. It's angry. Okay, how many valence electrons does chlorine have? I'm still looking for a periodic table I don't have. Here it is. Okay, 1, 2, 3, 4, 5, 6, 7. So chlorine has 7 valence electrons. Okay. Nope, not going to do it. Okay, there we go. So here you go. 1, 2, 3, 4, 5, 6, 7. How many does chlorine want? Chlorine wants 1. How many does hydrogen want? Hydrogen wants 1. Okay. Can we fix that? I think so. Let's make it in blue. So if we make a little bond right here, like so. Oh, look at that. Now chlorine thinks that it's got 1, 2, 3, 4, 5, 6, 7, 8. Congratulations. And hydrogen thinks that it's got 2. Nicely done. So now we got that guy. Okay, let's do a couple more. Let's do sulfur over here. So we need to look at the periodic table. Sulfur, there it is. So now we know that it's 1, 2, 3, 4, 5, 6 valence electrons. Okay. I'm supposed to be able to go right here, but it doesn't do it. I don't know why that is. Anyways, so we're going to go sulfur. Actually, that should be, let's see, clear all drawings. That should be, sulfur should be in red. Sulfur. Okay. And we said that was going to be, let's see, 1, 2, 3, 4, 5, 6. It's going to be 6. So we're going to go 1, 2, 3, 4, 5, 6. And now we need 2 oxygens. So we're going to have an oxygen here. We're going to have an oxygen over here. Okay, that's great. Let's look at our periodic table. Oxygen's right there, so that's 1, 2, 3, 4, 5, 6. So oxygen is 6. Okay. So you go 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. Okay. So sulfur needs what? Okay. So this gets a little bit weird, right? Oxygen needs an octet. In other words, 8 electrons. So it needs 2 electrons, 1, 2 here, and 1, 2 here. What are we going to do? Well, we're going to go ahead and steal one electron here. Let's try it again. We're going to steal one electron here. There it is. I'm going to steal another electron here. Okay, now oxygen has 1, 2, 3, 4, 5, 6, 7, 8. This oxygen needs to do the same thing. There's 1. And there's 2. And now sulfur appears to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And yes, that violates the octet rule, but that is the way that this weird one works. Okay? So let's see if I can draw this somewhere. So you would have sulfur, you have oxygen, okay? And they made not one, but 2 bonds with each one. So it's 1, 2, 1, 2. And then sulfur ended up with 2 electrons, 1, 2. And oxygen has 2 pairs. Just like that. So this is a strange one. This is a strange little guy because sulfur doesn't do 8 the way that it should. It should do 8, but it doesn't do 8. Right? Here's at 8. As you go 9, 10, should only be 2 more, but there's always exceptions to the rule. Okay? Let's clear that real quick. Let's do methane. Methane's a good one. These are all covalent bonds, okay? So let's do methane. Someday I'll figure out why that doesn't work. Let's see. So this is methane right here. So we need a carbon. And we need 1, 2, 3, 4 hydrogens. How many valence electrons per hydrogen? 1. 1. Okay, how about carbon? Well, carbon has 1, 2, 3, 4. So 4 valence electrons. So we go 1, 2, 3, 4. Now we're going to do our sharing. We'll share 2 here. We'll share 2 here. We'll share 2 here. And we'll share 2 here. Now carbon has 1, 2, 3, 4, 5, 6, 7, 8. And each hydrogen has 2. So it looks like this. Carbon to hydrogen to hydrogen to hydrogen to hydrogen. Just like so. Okay? Okay. So quite a bit in covalent bonding, huh? Let's go over to acids and bases. Okay. So substances that readily give up hydrogen ions in water are known as acids. Substances that readily bond with hydrogen ions are called bases or alkaline substances. Such substances release hydroxide ions. So here's a hydrogen ion here. That's an acid. Here's a hydroxide ion over here, OH minus. Okay. We describe acids and bases in terms of pH. Acids have a pH below 7. Bases have a pH greater than 7. A solution of exactly pH 7 is considered to be neutral. And here's a scheme for you to see what it looks like. Okay. So we said the pH goes between 0 and 14. 0 is highly acidic. 14 is highly basic. And battery acid, sulfuric acid, is close to pH 0. Hydrochloric acid, the acid in your stomach, HCl, is a pH of 1. Lemon juice, vinegar, about pH 2. Grapefruit, orange juice, soda pop, pH of 3. That's why we should stay away from soda, because the pH is very, very low and it can hurt your stomach. Aspirin is the same way. Aspirin is a very strong acid. So if you're in an aspirin regimen, you have to take just the right amount. If you take too little, it won't do anything. And if you take too much, it'll hurt your stomach. Tomato juice, about 4. Coffee, rainwater, about 5. Urine, saliva, milk, about a 6. Pure water, 7. Seawater, 8. Ammonia is 11. Soapy water, 12. I don't know if you guys have seen that commercial where they test, I don't know, like 100 soaps. And the only one that doesn't come out alkaline is the oil of Olay soap. And it makes me laugh every time I watch that commercial, because by definition, soap is an alkaline. If it doesn't have that alkaline in there, then it's not going to clean anything. So oil of Olay might be soothing your skin, it might be smoothing your skin, but it's not washing your skin. So I don't think they tell that to anybody though. So soapy water is about a 12. Bleach, oven cleaner, about a 13. Drain cleaner, which is lye, sodium hydroxide, is a 14. So you want to stay away from both ends because they're both scary. Blood is about 7.35 to 7.45. So we're slightly alkaline. Okay, organic compounds. Okay, why do we care about organic compounds? Because we're in an environmental science class. We care about ecosystems. We care about organisms. We care about the cycles of the world. And in order to understand the importance of these cycles, it's important to understand why we need these things for life. Okay, so organic compound now is understood to be anything that has carbon in it, but really organic means something that comes from life. Okay, so if it comes from something that's alive and has carbon in it, then it's an organic compound. If you have a choice between sugar and carbon dioxide, sugar is an organic compound. Carbon dioxide has carbon. It comes from life, but I wouldn't really call it an organic compound because it's a waste of life. Okay. So the 4 main categories: lipids, carbohydrates, proteins, and nucleic acids. Okay. First of all, monomers build up polymers, and that's true except in lipids. So a mono means one, mer means unit, forms polymers. Poly means many, mer means unit. And again, like I said, that is true of all of them except lipids. In lipids, what you have is hydrocarbons that consist of a fatty acid, 3 fatty acids actually, and a glycerol backbone. Okay, so effectively it's 3 fatty acids and a sugar. So those aren't monomers into compounds. It's only three units. Now carbohydrates, sugars are different. Okay, so sugars and starches. A sugar is usually a monomer or a dimer, meaning that it's 1 or 2 units. Starches, glycogen, are polymers. Okay, they store energy and provide structure to cells, like in cellulose. Cellulose provides structure to cells, but it's also energy for animals such as cows and horses. And they consist of long chains of simple sugars like glucose. Okay. Protein, if you want to know about life, you need to know about protein. Protein consists of 20 amino acids, okay? Those amino acids are folded in a very specific three-dimensional shape, and the three-dimensional shape determines the structure and therefore the function of these proteins in the cell, okay? They can do anything. Proteins are incredible. I call it God's Lego set, okay? If God had a Lego set and you build it one way, you can make a gun out of it. You can build it in a different way. You can make a cell phone. You could build build it in a different way, and it would be a car. You could build it in a different way, and it'd be an airplane. And that's pretty close to the way that it works with us. We have only 20 amino acids. With those 20 amino acids, you can make an immune system that protects you from bacteria. You can build a brain and vocal cords and lungs so that people can communicate with each other. You can build legs so somebody can run. You can build wings so somebody can fly. I mean, the fact that all these things, all these diverse events are made out of only 20 amino acids is mind-blowing, okay? But that's where it is, proteins. And then nucleotides, okay? They're made out of a carbon sugar, a phosphate group, and a nitrogen-containing base. There's only 4 main ones, okay? And they consist of RNA and DNA. They store genetic information and are frequently used as energy as well. So DNA consists of the nucleotides guanine, cytosine, thymine, and adenine. RNA consists of the nucleotides uracil, adenine, thymine, and adenine. So 4 nucleotides apiece. That's what they look like. So here's a hydrocarbon, like a fat. You have a carbon with hydrogen around it. Here's a sugar. A sugar has a C1H2O1 motif, which means that you're going to have some addition of a carbon, 2 hydrogens, and an oxygen. And the reason is because the sugar has a lot of hydroxides in it, which make it function as either a sugar or an alcohol. Here's an amino acid. An amino acid consists of a central carbon, a hydrogen, a side chain, an amino group, which means a nitrogen-containing compound, and a carboxyl group, which is a carbon with a double bonded oxygen and a hydroxyl group. So this is one amino acid. We have 20 of them. And then this is a nucleic acid. So it consists of a ribose sugar, a nitrogen-containing base, and 3 phosphates. So this one is adenosine triphosphate, and it's also used for energy. Okay, and then the nucleotides can be built in a double, and then an anti-parallel helix called DNA. Okay. So I don't know if you caught on to this, but each one of these things makes us need certain items. Okay, so let's go back to recapture this real quick. We'll go right here. So if you need fats, okay, if you need fats, what do you need? You need carbon and hydrogen. If you need sugars, you need carbon, hydrogen, and oxygen. Effectively, carbon and water is really what we're saying. If you need amino acids, you need a source of nitrogen as well, okay, and a source of sulfur. And the reason for that is because there's one amino acid of the 20 called cysteine that has a side chain that is sulfur, and is important because it creates very strong bonds, okay? They're called disulfide bonds. And then nucleic acids, well, we need carbon, we need water, we need nitrogen, and we need phosphorus. See the phosphorus here? So because these are the precursors to life, okay? Fats, sugars, proteins, and nucleic acids. And we need to build these for life. That means that we need a source of carbon, we need a source of water, we need a source of nitrogen, and we need a source of phosphorus. Otherwise, we won't be around, okay? So look at this: carbon, hydrogen, oxygen, nitrogen, and phosphorus, the precursors to life. CHON. We used to use it as CHONP, CHONP, the elements that are necessary for life. Okay. So you need to keep this in mind, because when we go into the geochemical cycles and we're talking about water and carbon and nitrogen and phosphorus, you're asking to yourself, why do we care? This is why we care, because we need these items. Okay. So we're going to stop right here, and I'll come back in a little bit. Thank you.